Hi, everybody. Welcome to our webinar. My name is Sarah Lynch. I am the marketing manager at Psim, and I want to thank all of you for tuning in today and sharing your valuable time with us. We have prepared a very special presentation for you, but before we start, I just want to go over a quick couple of housekeeping rules, and that is your go-to webinar panel you should see on your screens right now. There you have a questions tab. Please open the questions tab, and during the presentations, whenever any comments or questions come to mind, you can type them in there right away, and we will be here to answer them unless they will be addressed later in the presentation. And in the end of the webinar, we will have a Q&A session where we will answer the rest of the questions, and you can ask more then too, but please don't hold back, ask away during the webinar as well. Your questions are also private, so only us organizers can see your name, and we will not share that with the rest of the webinar, so please don't be shy, ask if you have questions. And finally, this webinar is being recorded. We will send the recording to you in the beginning of next week. So if you cannot stay for the whole hour or you want to rewatch some of the content that we go through today, we will have you covered, and we will get the recording very soon. Yeah, that's all about our housekeeping. Now I just want to quickly introduce our presenters for today. We have our very, very special guest today, Dr. Raymond Ridley. He's the president of Ridley Engineering, developer of RidleyWorks, and many of you probably also know him from his power supply design workshops and other educational seminars and presentations that he holds worldwide. And you might also know Denise Ridley. She's in the background and will help us answer some of your questions. And of course, on the Psim side, we have our own Albert Dunford. He's a power electronics engineer and a Psim specialist, and will answer all the questions you might have about Psim. Yeah, Ray and Albert will be your presenters today and walk you through our brand new and seamless integration between RidleyWorks and Psim. Good morning, guys. How are you?
Good morning.
Hi, good morning. I see there's a few people with questions about sound in the chat. Can someone please are there some other folks who are online? Can you just type in the questions if you're hearing us properly? I wonder if these are localized people with settings that need to be properly set up. Okay. There's lots of people who have sound. Okay, so I'll just deal with these people. Sorry. Yeah.
Yeah.
Right.
Just please click on your audio settings and make sure you have the right speaker or headphones attached or connected to the GoToWebinar app, and then you should get sound.
Okay, thank you,
right.
Sarah. Good morning, everybody from all around the world. I hope you're all safe and healthy and hanging in there during this quarantine. We're in California. Albert is in Canada. Sarah is in Florida, and I see attendees coming in literally from all around the world. So we have a great session here. This is my first attempt at doing this kind of thing that isn't just PowerPoint. So I'm sure things will go wrong and be interesting as I run 7 pieces of software on my computer, and you can all follow along with that.
I have every confidence in you, Ray.
I'm sorry?
I have every confidence in you, Ray.
I do. It's my computer I have less confidence in. So this webinar is actually a culmination of I think it's been a whole year since Psim and Ridley Engineering met last APEC in 2019 and sat down and said, hey, we've just built some links to LT Spice. Wouldn't it be great to link to Psim as well? And that's when we started talking about it. And I'm not sure Albert knew exactly what he was taking on at the time. It's been a fairly intense year. Well, but here we are.
Yeah, it wasn't too bad. We definitely generating the templates, I think, was a lot of work because there's a lot of stuff that RidleyWorks can export. I think the interesting part kind of happened more so over the winter when we started improving the sweep. Ray said that this needs to go faster, and we said, well,
Right.
let's go faster.
So here we go. Let me get started, because we have so much material here that, quite honestly, this could be an 8-hour webinar that we're going to cram into just about 50 minutes here. So I apologize, it's going to go fast, but over the course of the year and the summer, as you're all locked in there, we're going to do a lot more webinars going into detail into different aspects of the relationship between Psim, RidleyWorks, the design part, the simulation part, that you can all get used to using. So here's the structure of the RidleyWorks software, which kind of lives in the middle of our teaching world, our design world, and when we're doing consulting, it's our go-to tool. So the main point of this webinar is to talk about the links to Psim, but first we really need to set the stage of the differences between Psim, LT-SPICE, the difference between simulation and synthesis of a circuit. So in setting that up, I'll be talking about how RidleyWorks designs a power supply for you. You just put in your specs and you immediately get all the components of your power supply. It will do simulation for you. Psim is a simulator, LT-SPICE is a simulator, and RidleyWorks is a simulator too, and we'll point out what the difference is between the three. We have a link to LT-SPICE as well as Psim. We'll talk about why we do that. And then, of course, one of the big features we have, anybody that's been to our workshop knows that we do the magnetics design for you. And the whole point of RidleyWorks is to go fast. We don't wait 3 weeks to a month for a magnetics vendor to send you parts so you can start your power stage. When we do our workshop, we expect you to design the magnetics, wind the magnetics, measure them, and put them in the circuit within the first 2 hours of the workshop. So that's what our software is all about on that. And we do that at many levels. We go in really deep if you want to look at proximity loss, winding loss, very complex mathematics that are embedded into our software. We also do control. We have control transfer functions embedded in RidleyWorks, and then we're going to talk today about how we can do that in alternate ways, both in LT-SPICE and in Psim. And that's really where the strength of Psim comes along, since it has about 100 times the speed of LT-SPICE. So we will show that. Let's start at the beginning. We didn't run a survey on this, but I think if we did one, because
Ray, let's run the poll right now before we go too further along.
So when we always ask in our workshop, which piece of software do you have for simulating your converters? And the first answer always is LT-SPICE. And it doesn't matter how big the company, what their budget is, always everybody has LT-SPICE. And of course, the reason for that is it's free. And, that's not just a trade answer. There's lots of free software out there, but you need free software that actually does a pretty good job. And LT-SPICE is amazing in what it can do in its small signal simulation and its transient simulation. It's really come a long way under the guidance of Mike Engelhardt in speeding up the problems of LT-SPICE and avoiding convergence errors and working really well on switching power supplies. And that always has been historically a big challenge for LT-SPICE. But LT-SPICE does have its limitations. Everybody uses it. Everybody should use it. If you find you're at a university where you have Simplis or Psim already or something else, learn LT-SPICE, because when you go to work, everybody's going to be LT-SPICE. And it's not that these tools are exclusive. I work here, therefore I won't work there. These are all tools that you need in developing converters in a fast way. So where did Psim come in? Okay, Psim, it's on the same level there as LT-SPICE in that it is a general purpose circuit simulator. It does small signal simulation, just like LT-SPICE. You want Bode plots, you get Bode plots. Here's the strength. For power electronics simulation, it's what Psim was written for, to overcome the convergence problems and the speed problems of LT-SPICE. And the benchmarks that I'm getting now, and I think most people are getting, is about a 100 times speed up versus LT. And depending on what kind of circuit you're trying to simulate, that can be essential. Sometimes it doesn't matter that you go a bit slow because you get to study the waveforms while it's running. but that will be crucial for the work that we're going to show today. And then the other big features of Psim that take it beyond many of the simulators, it's got embedded digital control coming with it. It's got code generation in it. I don't know much about that. I think Albert can answer that during the question and answer session. And if you want to do really complex power systems, if you've got multiple parallel converters, you'll find LT Spice can, bog down pretty quickly if you've got really complex power systems. So that's where the strength of Psim comes along. Now, Psim, LT Spice, how does they talk to each other? Of course, I think Albert and Psim recognized, if you don't talk to LT Spice, then you can't play, because everybody ends up with their designs in LT Spice to share them around the company. So they port all their designs into LT Spice as well. Where does RidleyWorks come in? Well, first of all, it's not just a simulator. Simulation is secondary to RidleyWorks. It's an expert system. The programming began about 40 years ago in RidleyWorks. Everything I know about power converter design is embedded in the software. So it's actually going to design the system for you. That means the power stage design, control design, magnetics design and modeling, and it does it at a depth that no other programs can do at this point. It does small signal analysis, just like LT Spice, just like Psim. It does high-speed simulation. Psim is fast. It's about 100 times faster than LT Spice. We're about 10 times faster than Psim because of the very special algorithms that we have in there. So why do we need LT Spice and Psim? Because we can only simulate a fixed circuit. We synthesize a circuit, and therefore we have to know every single element of that circuit, understand how it works. We can simulate it very quickly, but I haven't met an engineer yet that doesn't need to change a circuit and add some op amps and add some other functionality. So that's why we port. First, we went to LT Spice. That was complete about 1.5 years, 2 years ago. And then we saw we needed the speed of Psim. So we port down to there now as well. And then one other thing we do is we do instrumentation control of our own frequency response analyzers. So that's the structure of the three. So my toolkit is all three of these pieces of software. Sometimes I need LT, sometimes Psim. Always I'm using RidleyWorks to feed those two programs.
Ray, let's before we go on, let's launch the poll, and we'll just get a feel for what everyone else is using. So Sarah, can you launch that up so everyone just select which one you're using right now, and then you'll get to see afterwards. We will, you'll get to see the results of this. So we just need to keep that up for a couple seconds, and then Sarah will publish the results afterwards.
Great. So there we go. LT Spice is running away with it as usual.
Yeah.
Second is Psim, and then RidleyWorks. Okay, I'm going to jump out of PowerPoint now. You'll be happy to hear because it's not a management thing there.
Ray, she needs to close the poll, and then before they can see back to your screen.
Okay.
Yeah. So Sarah, do you want to? Yeah, there we go.
We back to my screen?
No, she's showing the results so everyone can see the poll results, and then so LT Spice there, as you saw, at 70%, Psim at 32.
Great. Okay, you want to get me back, Sarah?
Yeah, you're back.
Okay, so here you go. Here's the entry point to RidleyWorks, and you can either begin design with this button here, or you can control our two frequency response analyzers if you don't feel like doing a design there. Let's go into the design mode right now. So here we're starting out with a 2-switch forward converter, and the beginning point of any power supply design is to enter your specifications. So here we see it's a 36-watt converter, 55 volts in, 100 volts nominal, 130 volts max, 12 volts output, 3 amps output. So a 36-watt converter. And this is a real consulting design that we did starting last December. You want to design a converter, you click OK. And it's going through. And the design is done at this point. It will recommend a switching frequency to you, 183 kilohertz here. you have the option of changing that. That's an odd number, so this design takes it up to 200 kilohertz. Okay. And then we have the choice of topologies that are in the program. We've got the buck boost, the boost that can't work for this application, single switch forward, two switch, half bridge, full bridge, push pull, and flyback.
So Ray, if I could ask a question here, why did you choose these particular topologies, and how do you feel that they cover the market with regards to used converters?
Well, we do a lot of consulting out there, and I would say most of our consulting, believe it or not, is on flyback converters. People build a flyback converter from an app node or from power integration or somewhere. They have trouble when they go into production, so we help there because everybody needs a bias supply. So in terms of the work we do, I'd say the flyback is number one. But in terms of number of converters built, the buck converter is number one in the world because every point of load power converter has a buck converter. Shifting a little bit these days to resonant, isolated converters, but still the buck converter is predominant. We like the two switch forward because our job is doing a design as fast as we can. As a consultant, if you don't get in and get out quick, the customer's not happy and you can't make any money. If you're doing a design in-house, you just want to be sure that your converter is going to work. And a two switch forward for us is the fastest design route for anybody. Might be a little overkill sometimes, but it's a question of a trade-off of your time versus the cost of the converter. So we're going to do an example on that one today because it incorporates the transformer, the inductor, full isolation, and then everything that we need to see here. Okay, so once you've entered that in, and that's like a 5-second process to do that, you immediately go to the circuit and you say, click on a waveform. There is the startup of the converter. Let me do that again. So this is the simulation speed. Ready? Right, go. Done. You want to continue to get to steady state? Let's continue at steady state. So that's 400 cycles of simulation, which is basically, it's as fast as Excel can plot the results. If you want to do some more interesting things like step loads, click on the 10% to 100% step load, and there you go. So you have a step load design already. Now at this point, you haven't done any design. It's all been done for you. The inductor is chosen, the capacitor is chosen, the transformer is chosen, the loop is closed and optimized. In this case, it's current mode control. Everything is done on your converter for you. You can do some interesting things. If you don't like the overshoot here, this is about a 10% overshoot during a really large step load. If you say, okay, well, I don't want that much overshoot. Let me fix the scales here so the same. If I want to reduce the overshoot on this converter, basically I have to increase the capacitor. So I can increase the capacitor and watch the simulation on the same time. Now this is not something you can do inside LT Spice because every time I change my capacitor, I recompensate the loop automatically, then I simulate. So there's a lot more going on than just changing the value of a cap, changing a parameter value. It's doing a re-optimized design for the converter.
So let's clarify that one more time, Ray. So when you change the cap value, you're recalculating your control characteristics. So that's everything from what does the slope compensation change for the peak remote control, and it's just the loop, the type 2 values?
Everything that needs to change changes. Okay. I mean, a lot of time people say, well, can we get those design equations? And it's like, well, which ones do you want? Right. So they say all of them. I said, well, we have 3,900 design equations at this point after 40 years of doing this. So everything changes that need to. So look, here's your compensation values. It actually tells you what the compensator is. If you reset to the original cap and you pull that up again, there'll be different values in here. Okay, this is really important because you'll know that if you just add capacitor to your power supply that's got too much overshoot, nothing happens. The overshoot stays about the same because the loop gain has gone down at the same time as the cap is added. So you have to do all these things at once. That's the power of working here inside RidleyWorks. Nowhere else can you do this kind of thing. You can answer other questions like, well, what if I didn't use current mode? So many times I see papers talking about current mode or voltage mode, which one's better? Well, this is better for that, this is better for that. Just answer the question, here it is, here's voltage mode. Okay, you see it has quite a different transient response, and then this is back to current mode again. Okay, on a step load, they're about the same. If you want to know why you always use current mode, go to steady state, do a line step, and you see there's almost no perturbation with current mode. And then if we change it to voltage mode, there's our voltage mode. So voltage mode, current mode. All right, that's why every self-respecting converter is current mode control. But these are not, every time I'm changing voltage mode to current mode, we're optimizing the loop at the same time. We're not leaving the compensator the same. So you can definitively answer the question like this inside RidleyWorks.
And,
okay.
Just to clarify how that would work with simulation is you'd have to have individual circuits for each scenario that you're just clicking through, which would get quite onerous to have lots of different simulations working, to have multiple things all laid out already, which is very handy to have all inside of this one tool.
Yeah. So when we redesign a loop, if we're down in Psim or LT-Spice, we go back up to RidleyWorks, recompensate the design, export it back out again to LT-Spice or to Psim. Okay, let's do that. Right now, what we're going to do is click on, let's go Spice Launch first. So here we're going to take that circuit that we've just designed and send it over to LT-Spice. Okay. Let's make sure, am I still voltage mode or current mode? Current mode, okay. Now we go into LT-Spice. So we enter this familiar design environment for you. Do file, forward converter, oops, not sweep, not that one. File, transient, and then we run LT-Spice on the same circuit. Here's the startup of our converter. Usually it's taken a little while to get there. Here's the startup of the converter inside RidleyWorks. So right now what we've done is we've reproduced the waveforms inside LT-Spice. And if you're just starting converter design, if you're new to this field, generating that very first schematic is a horrible job. You've got to figure out how magnetics work. You've got to figure out how the switches work. Should you use ideal switches, real switches? And getting the circuit to converge at the beginning is a long and arduous task. Probably take you about a week first time you're trying to do this with switching converters. That's the point of our program. We take you from spec to Spice simulation instantly. Just a click of a button, a few seconds, you're in there. So that's our LT-Spice.
There's a couple questions before we go further here. So there's a question about varying the ESR in RidleyWorks. Is that a design possibility in this?
Yep. You click on the cap. You can ask it to do it at a high level for you. You can use multi-layer ceramic or you can use low-cost caps. Here you can enter the specific capacitance, the specific ESR of the cap. Okay. So you got full control over every element. We don't lock you into anything.
Yeah, and are you plotting output impedance at all as one of your outputs? Or
when we move on to control design, which is here, we've got output impedance, audio susceptibility, or PSRR. So yes, both of those. Okay, great. So you can even go to the output impedance, plot that either log scale or linear scale. It shows you open loop, closed loop. You can change to voltage mode from current mode. So you can do all these comparisons,
And there's also a question about snubber networks.
Snubber networks, absolutely. We do snubbers as well.
Okay, great.
I'm not going to touch on that just because we'll get hung up on these. But yeah, that's part of our workshop. You design the magnetics, you put them in the circuit, put the snubbers in. But we have a snubber design button that you can turn on as well for all kinds of different snubbers. Okay, now we're going to go to Psim. We link to the same circuit to Psim. Okay, and it's right there. So now we open up Psim, and then here the circuit has come in. Let's make sure inside here, when you click on the file, you get all the parameters of the circuit. The sweep flag tells you if it's 0, it's transient. If it's 1, it's frequency response. So we're going to run that same waveform inside Psim now.
Right, so just while you're doing that, let me just chime in here. So the LTs, you generate a set of LT spice simulations, one for the transient and one for the sweep.
Correct.
With the Psim templates, it's one circuit, and that circuit, in the parameter file, there's a setting that you change, which Ray just did, to toggle between the transient and then the sweep.
Right, exactly. So here's our transient inside Psim. Let's run that again. So you get an idea of the speed. That's 1 second, 2 seconds basically, but we're doing 20 milliseconds inside Psim. So that's 4 times the length of simulation that we did inside LT Spice. So that shows you the speed that you're getting here. So again, I know lots of you, I think it was about 1/6 the number have Psim as have LT Spice. And I know you have the same barrier as me. Learning a new simulator, you just don't want to do it at some point in your career. It's like, okay, where are the symbols? How do I draw this? How do I optimize the circuit? We're designed to get you past that hump. Okay, so it puts out the Psim circuit for you. Click on the button, you're already running. So you can go from spec to Psim simulation in about 1 minute when you know what you're doing here. So it just compresses that whole part of the design phase for you, and then you can get on with the circuit design. Now you can come into Psim and add any elements that you want to inside this circuit. Okay, let me go back to PowerPoint for a minute. So there's our design example we just went through. There was a step load response that we went through, increasing the capacitor. And then we exported to Spice, about 100 times speed up when you went into Psim. Now let's go look at magnetics. Because magnetics is still the deep, dark mystery to almost everybody in power converter design. There's a fairly small percentage of people that really get magnetics. Those of you that have been to our workshop, probably about a 10th to 5th of you have been to our workshop, you know that the big mystery, the big secret of magnetics is actually pretty easy. And we get people winding magnetics quickly in the course, design them, wind them, build them, and test them. So this is how we do it. You just go to the magnetics design page. You start by choosing your core, and it will tell you for that application, here's the core area that you might want to use. Any core that is that area is going to work for you. Here is a library of cores. Go choose something that's about that area, whatever your favorite core is. If you don't see your favorite core in there, we give you up to 40 custom cores that you can enter. That means you've got to do a little bit of work. You've got to extract the data and put it into our program to make it work. So for that core area, we'll use the generic core right now. We won't go specific. It tells you you need 25 primary turns. You need 13.5 secondary turns. Can't do that. Change that to an integer, which gives you 13 turns. And then that is your basic design of the transformer at a high level. So we've got the turns, the core. Now you look at the core material. And when you've been doing this a long time, you realize that just about every ferrite is the same. They're all different core losses. Here's an F material, sorry, an F material, a P material, a PC95 material. And when you're looking at the loss in magnetics, always go back to the waveforms. Make sure you're in steady state. So let's go to steady state. Otherwise, it's evaluating, oops, just do my line load step. Okay, come on. Continue. Okay, there's the steady state of my converter. Now we'll go back to the magnetics. look at the core material again. And you can see here's our loss in that core. It's not very high.
So tell me, Ray, that RL ladder circuit that gets exported,
Right.
that you can export to LT, and we also support it in Psim. How does that run in LT when you export it?
It runs, it's a strange network in that we've got some very, very large resistor values here and some very, very large inductors. So LT Spice struggles a little bit with things that are switching at the nanosecond scale, and then suddenly it's got these enormous time constants associated with the core. So we always give you an option, enable the LT Spice model or disable the LT Spice model, because we can't guarantee this is always going to converge. But when it does, it's a thing of beauty because you no longer have to go look up the curves for these core materials. You've got a SPICE model, you click on the SPICE model or the Psim model, it tells you what your core losses are. You will see it change with duty cycle, you'll see it change with how you drive, how fast you drive the core, and it just captures all the characteristics of that core. You know, it's going to be at a specific temperature, but you know, this is quite new, that you don't have to go back to the archaic way of looking at core loss curves, which is about 100 years old. We're trying to move this into the 20th century, if not the 21st. So that's what we do with our core material. Now let's look at the windings. So here's our primary winding. And it will tell you when it starts the design, it needs 26 turns. You can wind this with one layer of 29 gauge wire. Here is your winding loss. And our winding losses are two parts. There's DC resistance, AC resistance. This looks like a very simple structure for how you lay out the windings in a core, but it gets involved in proximity loss. It tells you how many skin depths you have here. It tells you your resistance multiplier by layer. If you want to know how complex RidleyWorks gets, here's the proximity loss equations. These are Dowell's equations from 1966. Our estimate is about 0.5% of design engineers get this and really use it. Okay, so it's all embedded for you. If you're using RidleyWorks, you're doing proximity loss analysis. Very, very advanced stuff. When I started my career, it took me 10 years before I got into proximity loss because it's tough to understand. When we do that, we can look at the resistance, and I haven't run the model on this to match yet, but we predict what the resistance versus frequency is going to be, and then we give you a network which will match this curve. Okay, I'm not going to run that because I said, well, let's run it. Let's run it.
While it's running, we've got a few questions, Ray.
Okay.
There's, can you choose what kind of wire types? Is LITs an option for the magnetics windings in your tool?
We have the options of magnet wire, triple insulated wire, and foil at this point.
Okay. There's a question about specific temperature, but I don't know when that, there's a question about order of the windings. Is it possible to select the winding order of winding?
It doesn't really matter which one you put on first. The proximity losses are approximately the same. Obviously, when you wind the second one on top of the first, the winding length is going to be a little bit bigger. We don't really look at that as a big driver. I mean, when I'm winding a magnetic, it's not about the esoteric analysis. It's like, which winding has the higher turns count? That one goes on first, because you can keep that neat and flat. If you've got great big bulky wires or foil, you know, once you put them on there and then you wind the fine wire after it, it doesn't work out so well. But here you go. What we've just done now is we've matched the AC winding loss with the proximity loss model. Okay, so we've introduced 5 inductors, 5 resistors, and I don't know why my values didn't get populated here. Yeah. They should have done. But these values get populated, they get calculated, and then you can see the match. Let me run that again.
So then there's a couple other questions here about this, about temperature of the magnetic stuff. Yep. Is this all assuming room temperature, or are you changing temperatures?
We can do all those things. We start at room temperature. The wire doesn't make a lot of difference. The coefficient on the wire is fairly small.
And the cores?
couple of 100 degrees C, it matters, of course. And when we look at the core losses, it will either use the 25 degree C model or it will use the 100 degree C model for extracting the core losses, because there's quite a difference there. Okay.
Okay.
All right, good. So when we go back to our PowerPoint, we've done all that very complex analysis, just a function of putting it into the program though. So we go through all that complex analysis for you. You do proximity loss, and we plot this curves. Here you can see our value is properly populated. So you see here, we start out with 69 milliohms. When you're getting between a megahertz and 10 megahertz, that becomes a 9 ohm piece of wire. And then here's the inductor values that make that happen with the right shape. And the beauty of the Psim link, sorry.
There's a question about asking if this all exports into Psim, and there's your slide.
I'm sorry, I didn't understand that, Albert.
Sorry, there's a question about if these models exported into Psim, and then here's the slide. You were getting right to it. Sorry.
Right, right. So you have the option of exporting those models or not exporting those models. So every time you see a resistance of a secondary here, you can export the proximity loss model as well. Here's the primary, the proximity loss model, inductor ESR, and the proximity loss model. There's also a core loss model on the inductor and the transformer. These are optional, whether you export these or not. Obviously, they're going to slow down the simulation, because if I exported all of these, I would have 5, 10, 15, 22 state variables to add to the simulation. Psim can handle that just fine. LT-Spice does an okay job. It's not that slow, but it definitely slows things down. So when you're looking for these losses, you include them. When you're running a sweep on it, if they're not going to change the sweep much, you can take them out or you can include them. You can also do some experiments that have never been published. You can sweep the control to output transfer function of a converter with proximity losses. Nobody has ever done the math on that, of how much the proximity losses change the damping, the Q of the filter. So that's some interesting things that Psim can do for you. So all of this magnetics modeling, you don't have to know every detail of what's going on in there. Everything is brought out to Psim. You run Psim and you've captured all the results on your circuit. Let's talk about, that's magnetics. We'll have a webinar, by the way, on just magnetics design, because it's a very deep topic. Let's talk about small signal. This is the original converter. It's a 2-switch forward converter. Here's my switches, my diodes. Here's some other diodes and a transformer in the way. If I want to get the small signal of this, the loop gain of this, classically, what do? We generate the small signal model. And this is the small signal current mode model. It's got Volparian switch model in the middle. It's got a modulator gain, some feed forward terms for input and output, current sensing gain, and that one, what we call a sampling gain in the current feedback loop. These are the parameters that go into the model. Now, if you're just coming into power electronics, you're doing your first design, you say, well, how does this relate to this? There's switches and diodes. What is this switch model? What is the correlation between these two? And if you want to find out, go read this book. It's 200 pages. It will tell you where that model comes from. Now, when I'm designing a converter for real on a consulting job, do I use this model? Well, I use it inside RidleyWorks, but do I generate the SPICE model? Well, I wouldn't if I had to do it by hand, because even though I invented this model, I can't remember how to do it. I don't know what that value is and that value is and how I implement this value. This is a very reduced circuit to get down to here. So small signal, yes, we have to do it sometimes. You've got unstable converters, complex power systems. But this mapping of a topology to a small signal model is complex. There's a lot of study that has to go on to get there. It's done for you anyway. This is going back inside RidleyWorks. So let's jump back inside the program rather than PowerPointing this. I'm mindful of the clock here too to make sure we get to the punchline. Here's our control design. We look at the loop. Let's start with voltage mode, so it looks familiar. Here's our voltage mode transfer functions. Let's just look at the power stage first. Great, there's a power stage. Everybody knows this. You'll find it in any textbook. What does it look like? Here are the poles and zeros and the Q. Here's the DC gain. What's the equation? Here's the equation for all of that. And thanks to Dr. Vorperian, who helped generate all the equations that are in here. They're more complex than you'll find in most textbooks. You can always use our program as a reference for these equations. It's a convenient way, because if you go to any textbook and you read up what the control to output of a buck converter is, they're all different. They all use slightly different notations. Here's a convenient way to find it. We can do some interesting things inside our software here. It's like, okay, let's change the inductor. Let's nudge the inductor up. And you can live watch the control transfer function move. So we have this nice interactive feature here. So before you all go and start programming up those equations yourself, you'll never get to this stage where you can make all this interactive. We can change the input voltage. We're at minimum now, bump it up to maximum. And then the gain jumps up and down when we do that. Not much else happens. We can change control mode from voltage mode to current mode. Okay, there's the current mode transfer function. Looks first order down here, becomes third order at half the switching frequency. So there's our current mode. Now we add compensation to that, and then we create the loop gain of the converter. We can do some advanced things like click on the compensation. We can reshape this and just watch the curves while we reshape. So here we are moving the zero of the compensation. You'll see the phase margin drops and the gain here, actively climbs as I shift that compensation zero. So a lot of fun things you can do graphically inside the program. There's no thinking about equations, what's the R's and the C's, that's all taken care of for you. As you shift the poles and zeros, the R's and C's move as well.
So, Ray, if I can ask a question here, you have a recommended cross frequency and phase margin for most of your designs. How did you come up with that? What is that? Just basically a rule of thumb, or what's your thoughts on that?
Inside our program, the crossover target for a buck-derived converter is 1/10 switching frequency. The phase margin goal is 50 degrees worst case. Okay, so if you can hit that for a real converter under all conditions when you're doing your prototyping, you've done a pretty good job. If it gets below 50 degrees, you start getting a bit nervous. Theoretically, is it still stable? Yeah, of course it is, but here we can go look at the meaning of that phase margin here. So let's do a step load on this little converter. We'll do a smaller one so it's not large signal ringing that goes on. So this is a step load from 100% power to 80% power. And now we can go in and start eroding the phase margin. So see, you're at 56 degrees, 55, 54, 52. See what happens here as I start cutting down below 41 degrees, okay? It starts getting oscillatory. It's fairly well damped, but do you really want to see this in your converter? So I'll see lots of app notes say, well, we can do 30-degree phase margin, it's fine. We can do 23 degrees phase margin, it's fine. The overshoot here won't change a lot, but you don't want this to start happening. And then, of course, if we start going too far with this, let's bring this pole down, Yeah. And of course, you get this weird thing where the phase margin doesn't quite correspond to when the oscillations come in, because you get large signal oscillations as well as small signal oscillations, all right? Send those back to our design point. There you go. Notice that the transient response in this direction, that's unloading the converter, is different to the transient response in that direction. Okay, you can't live in just the small signal land, because in this direction, all kinds of strange things are happening, such as here, this is the current changing. Here we're doing a step load increase, and you can see there's a slew rate limitation on the current there. The current can't move any faster than that because we've hit the duty cycle limit. If you look at the control signal, you'll see it hitting the rail right here. Okay, that's not in any of those small signal models. So living in small signal land doesn't help you. You have to do this large signal transient with the controller being simulated properly, and then that's what explains, you know, those asymmetrical responses right here. All right. So this is all the fun stuff you can do inside, you know, RidleyWorks. And that's our small signal. So this is the classic way. We have the equations, so we have the small signal model, and then we plot them. But what if you don't have time to do that? So you're in a hurry, you want to get the plot of the converter you've just simulated, but you just don't have time to generate the small signal model. Or you may be using a control scheme where you don't have a small signal model. And most of the time, you actually don't. So when we go back into LT Spice, for example, and we look at our current sensing network here, you see we're sensing the current with the resistor, and then we're putting a filter on it. That's to take off the leading edge noise. As soon as you do that, there is no small signal model that's valid. Nobody has ever analyzed that case. It changes, the gains change, the slope changes, but it changes in, you know, sometimes subtle, sometimes profound ways. So what can we do about that? Well, instead of using small signal models, we can take a large signal circuit, we put a frequency response analyzer on it, and we say, okay, just sweep the large signal circuit. So that's what we're going to do here. Fixed input voltage, fixed load. We put one of our analyzers on. This is the AP300 model that goes in here. Got all the parameters set up for that. And now we're going to sweep through that circuit. So click on the run button. And has to go through an initial startup transient to find its steady state. And then here we are. We're actually sweeping a 300 hertz sine wave on a 200 kilohertz converter. Okay, it's a little bit slow because it's LT Spice. It's got a lot of work to do. Sweeping through, we need at least 2 complete cycles of sine wave here. But to be fair to LT Spice, this was not possible 5 years ago. You would have waited so long for this to come out that you just couldn't do this kind of approach. Mike Engelhardt did a fantastic job of speeding up LT Spice and optimizing things, you know, using the multi-cores, whatever they do. That's not my domain. This is now possible, and it's faster to do this, even though this is fairly excruciating, than it is to read my 200-page book, generate the small signal model, do the plots, and then figure out why it doesn't agree with what you're measuring in the lab because you put filters on it that don't count. So this, even though slow, is going to be a time saver. Sometimes I like how slow P-Spice goes, LT Spice goes, because I can learn, I can look at these waveforms, oh, look, yeah, I'm shifting the injection here. I can look at the other point on the waveform here. I can look at here's the other signal. So we're asking LT Spice to plot the gain of this big signal here versus this little signal in blue. And let's delete one of those so you can see the blue signal. There's our small signal that we're looking at. Lots of ripple in there, lots of noise in there when we do that, okay? So LT Spice has got to go in there afterwards, cut out all the switching noise and just extract the main waveform in this. So it's kind of fun to watch these. If you're in a meeting and your boss is showing too much PowerPoint, just pull up RidleyWorks, run through a sweep, and you can entertain yourself in the meeting. So lots of people do that, and people will look over your shoulder and say, hey, that's really neat. What are you doing there?
Lots of hard
We're
work.
gonna leave. Go ahead.
I said lots of hard work.
Lots of hard work, yeah. So we're gonna leave LT Spice running there for the fun of it. Hopefully it doesn't bug us down too much. Now we're gonna go back into Psim again. Now in Psim, we have one circuit that does everything. We want to turn on the analyzer. all we do is change the sweep flag to a 1. And then we say, okay, get that out of the way.
That's
a little plotting issue there. Let me do that again. I was doing something else. So here's my sweep time, and it's taking 4 seconds here. I've already finished. This is going from 300 hertz. Sometimes this doesn't plot, Albert.
Yeah, let's check that.
I ask it to plot the same thing again.
Yeah.
And it brings them all in. So
yeah,
nothing going on. They're easy enough to fix. Here we go. Here's our loop gain, crossing over somewhere near 20 kilohertz. Here's the loop phase, which you'll find corresponds to exactly what you got inside RidleyWorks. So we're now reproducing the loop inside Psim, and we're doing it 4 seconds it took to do this. And can't remember if we've got proximity models going here.
Yeah, that should be the
Yeah,
flag.
we're not actually running the proximity models, but
You could.
normally this is about 2 seconds, because I've got LT Spice running in the background too. Let's see how it's doing, shall we?
Yeah, while we're waiting for LT, I could just quickly comment on what Psim is doing here. So one of the things that we worked on with Psim was in speeding it up was to ensure that so we're running the system to steady state, and then we're injecting the perturbations. And one of the things that we can do with Psim is we can multi-core the simulation. So Psim doesn't break the matrix apart to run on individual cores. So one simulation doesn't get broken apart, but what is happening with Psim is that we're running the individual simulations on the extra cores. So the more cores you have, the more simulations you can run simultaneously, and then potentially the faster this can go.
Right. Okay, while you were talking there, I had Psim sweep from 100 hertz instead of 300 hertz to show you here we're getting 60 dB of loop gain, which is pretty amazing that you can simulate those little tiny waveforms, then extract everything afterwards. Still crossing over the same. You see we now have a nice clean sweep here. Inside here are the settings of the analyzer. So we set all this up for you. So start frequency, stop frequency, the signal levels are crucial. Anybody that has our analyzers know that you have to set up a profile with the start and stop levels. You have to estimate where the crossover is going to be to set those levels properly. How many cycles you want to do? We do 3 cycles, we ignore the first one. And then we have a transient time. When you inject a new signal, you can't just start measuring in the simulator. You have to let 1 millisecond time out, then you run a cycle, then you collect 2 cycles. So this is really intensive work. Let's go sweep down to 10 hertz here.
And just like while you're doing that, Ray, so this parameter file that he's looking at here, this is basically the information from RidleyWorks on the design summary page. So you should be able to look back at RidleyWorks on his summary page there and see all of the same information, and all the same variables that are declared there should be visible here as well. And it will automatically update if you export again.
Let's go see how LT Spice is doing.
Yeah.
Okay. It's on run number 16 out of 44. I think Psim kind of boots out LT Spice. It takes control of the processor. So not entirely fair to compare this way, but I think you're getting the point here. Let's go back to Psim again.
Yeah. And this includes post-processing as well. One of the things that I've noticed with LT is if you end up with a lot of data points, is it can take a little bit of time to post-process on the measure command.
Right.
Whereas,
so right now we're sweeping at 10 hertz.
Yeah.
We have to process 60,000 switching cycles for 1 injected frequency, which is an enormous amount of waveform processing to do. And as it goes along, as Albert just said, Psim is extracting the data. When you try to run LT Spice on these large files, it runs the circuit, then it goes into the post-processing phase where it calculates all the waveforms that you got. So you generate these just enormous files, so, you know, many gigabytes large. I don't know if you do that too, Albert, or whether you wipe them out as you go along.
Actually, we're saving the individual runs, the transients. So if you go to the folder, you can see the transient responses for each one are there for you to look at.
Right. Okay, so here we go. You can see things chugging along at the bottom here.
Yeah, so there's a couple of questions here. So the Ridley box there, yes, that is actually, quote, doing something. That's basically a sub-circuit that has the sweep information behind it that we're doing. There's a couple questions about input and output filters. So the template automatically populates all of the parts that can come out of RidleyWorks, but if you look at the settings file, there's going to be flags that enable or disable them.
Right.
So in this example, I don't think we have an output filter and we don't have an input filter, if I'm correct, but those can be designed back in RidleyWorks if you were going to be doing those.
Yeah, absolutely. So in the basic template here, we've put in proximity loss if you need it. We've put in core loss if you need it. We've put in a second stage filter if you need it. And we put in the input filter. So the intent was to create one circuit that will work with all the different permutations from RidleyWorks. So as you build more and more complex systems, you can go in, you can simulate those, and it's really unlimited. And of course, you can add any circuit that you like to this. Now, you saw we were done there while we're talking. This is amazing. We could not have done this even 2 months ago because that's when we started the speed up process. So this was 2 minutes, and it's sweeping down to 10 hertz. Now, when you're doing a loop gain in the lab, you always start at 10 hertz. You see some people that make loop gain analyzers, they start at 100 hertz or 1 kHz because it's really hard to get a clean measurement in the lab below 100 hertz, but you have to go there. Even if you're switching at a megahertz, you've got to inject at 10. Why is that? Because you got line noise. You got 50 hertz, 60 hertz, 100 hertz, 120 hertz. If you don't know your line rejection at 50 hertz, you can't be in the audio amplifier business. Otherwise, you're going to get hum coming through the output. So loops, every the old HP machines, they always started down at 10 hertz. We've just done that in Psim. Getting 80 dB of gain in this loop, a really clean sweep, which it's almost magic to me, Albert, how you're doing this actually. But I'm shocked at how clean this is here in these very high gain values. And you might ask, somebody asked a pre-question about the time step we're using, and it's not that fine. This is 2. So 0.2 microseconds is the time step. We're not trying to do a variable time step here. Slow things down a bit depending on how we set up the parameters. But it turns out you don't have to be that critical when generating the sweep responses. Now, if you're looking for crucial timings and switching events and snubbers and things like that, of course you have to zoom in. But when you come out to the loop gain characteristics, we're getting this much gain without using a really, really critical time step. So that's very important.
Just to comment on how Psim runs on the fixed time step. So the way the fixed time step works is it interpolates whenever there's an edge detection with like a switch changing state. Even if that doesn't occur at an integer time step, we carry an error forward. So you should end up with the average values of the currents or voltages should be the correct values, even if you're not like resolving the time step versus the duty cycle perfectly. The way the dual step works is that toggles or that triggers whenever that edge is detected, it'll toggle the minor step to occur at that point. So there's a couple of things going on there too.
Okay. Now I see everybody's still with us. We're going to keep going. We're almost near the end now. Let's go see if LT Spice has been happy yet. It is on. It has finished. It has finished. Now, interestingly enough, LT Spice has always had the capability of sweeping loops like this, probably for about 10 years now. It's only just become viable because of the speed of the computers, the multi-core threading, and just the efficiency of the program. Notice here on the red waveform, you can see this contour. Let me not cut it. If here it's injecting a fixed signal, and then at some point it starts dropping the size of the injected signal. Okay, so running these sweeps on a simulation circuit is just like running them in the lab. If you don't set up your analyzer properly, you get garbage in, garbage out. If you overdrive, it distorts. If you get underdrive, you can't read the results. So you have to shape that injected curve as you go. All of that is automated with that Psim link here. Now, those of you that haven't been through this before, let me show you how you turn this into a Bode plot, because you probably won't guess this. You have to go to View, Spice Error Log, right click, Plot Stepped Measured Data. Yes. And there's your Bode plot. You all saw that coming, right? Why it's so convoluted, I'm not really sure. It's well hidden. It's in some app notes. You know, the fact it's there is marvelous. Just learn the trick and then you're ahead of everybody else. Add a trace, loop gain. Okay. There's your loop gain inside LT Spice. Okay. Takes a while. I think this simulation, I said, it's about 100 times slower than Psim. LT Spice is all you've got. Use this feature. Okay. But I encourage you to try the Psim capabilities too. Okay, there we go. Let's just jump back to here. Presentation. Yeah, so that's 300 hertz. 300 hertz in Psim is 2.5 seconds when it's got full control of the processor. 100 hertz is 8 seconds. And 10 hertz sweep is 100 seconds inside Psim. It's more than 3 hours inside LT Spice. I've never waited long enough to see if it got there, because I think it would fill up my hard disk drive, quite honestly. So yeah, you're not likely to do that. That's the power of the Psim. And remember, simulation is great, but you can't ship a simulation. When you're done with your analysis, your simulations, and hopefully you get to hardware fairly quickly, because you got to sweep the real circuit. People love to do simulations and then they got an unstable power supply and say, well, I don't understand. The simulation said it was fine. Simulation always might say it's fine, but always, 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 measured results are different from the real circuit. There's noise, there's all kinds of things going on with your circuit you can't predict. You're going to sweep the real circuit. We have 2 analyzers that can do this, right? IP300 you all know about. We've got the RidleyWorks, which is a little bit delayed by supply chain, but that'll be coming out soon, which will sweep these curves for you under different line load conditions. So yeah, always balance your time between analysis and simulation and getting the product out. You know, hardware, simulation should always track each other as much as you can. Okay, we are at, if you want to learn more, RidleyWorks, if you click on this link in the PDF file that you can download.
Yeah, let me just chime in. So there is a handout option somewhere that you can all download, which is Ray's slide deck, which he's gone through. And yeah, so, and then there's going to be live links in that as well. So you can just click on those links in there.
If you want to try a full demo of RidleyWorks, send an email to this address and we'll send you the link to download the full demo, the full version, not a demo version, the full version, so you can try this. And you're going to need Psim's latest version 2, the 2020A version.
Which is in beta.
Right,
it's going to be released
a little bit about that. I know some of you have the beta version of that. So that's where you can learn about RidleyWorks. Click on that, go to our website. If you want to come to a workshop, obviously no one's coming to a workshop for a while. We're going to have other options for you to actually do some of this yourself. Wind some magnetics. It's nothing like it for learning power converter design. Frequency response analyzers, if you're stuck at home, got a nice affordable option for you. If you're doing aerospace work, you know, these are shipping. Actually, we can't keep up with demand on those right now. Seems like everybody needs one at home. Come join our Facebook group, Power Supply Design Center. Okay, it is the most active power supply group in the world. And yes, I know it's Facebook. It's like, get over it. Facebook is evil, but invent a name for yourself. Come on, because they run wonderful groups and we have some great discussions on there. Resolve a lot of problems for people in their power supply designs. And this is David Edwards' Class D, isn't it? Where he's using Psim to find the distortion on his Class D amplifier inside Psim. And he's got RidleyWorks as well. Free book, download the free book. 200 pages. You got nothing to do. You're all at home. Read through that. Send me questions when you get stuck. And articles. There are a lot of Power Supply Design Center articles. So just click on this link in your file, and there's about 150 papers on there, practical power supply design tips for you. So come join the Facebook group. There's 4,000 engineers in there. We have Albert is on there to answer questions about Psim for you. We have Alex Lido. He's the president of EPC. If you want to use GAN, you can go on there, you can ask Alex Lido questions. So he's gotten over the Facebook fear, so you can do it too. Dr. Volparian is on the group. He's just kind of lurking there watching, but there's some very high-powered people on there. It's a great community to come learn things. And here's all your, sorry, go ahead.
Yeah, I was just going to say, David Edwards is asking to remind everyone why the Ridley box uses a 16-bit front end.
Say again?
Is asking for you to remind everyone why the Ridley box uses a 16-bit front end, although.
The Ridley box?
Yeah.
16-bit?
Yeah.
Well, it's a variable number of bits.
Oh.
Right.
Yeah.
Is my camera working? I can't see.
Yeah, it's,
right.
Yeah, you're on.
Here's the Ridley box. So this is a 200 megahertz scope, and it's a frequency response analyzer, 4-channel, and it's got RidleyWorks in it, and it's got a computer in it, and it's going to have a demo version of Psim in it. So it's everything you need in this test box, and that's what we created it for doing our mobile labs. So that was the intent of that. So the number of bit shifts depends on how many channels of the scope you're using, and so on. Did that answer the question? I hope.
I hope.
Okay, we'll have more sessions about that too. But let's see. Here are your links of Psim. There you go. You're advertising the brand new 2020A. So you got to put it out now, Albert.
Yeah. There's a couple bugs to fix, so that should be ready in May. We've got another webinar running, a Psim design webinar for LLC design, which we've got a new applications engineer, Amit Kumar, who did his master's thesis stuff on LLC design. It's got some interesting stuff, so come by for that. And then obviously we do a lot of stuff on LinkedIn and YouTube, and we've got this recording will end up on our archived webinar sessions, so check that out. And then there's a lot of people who mentioned motor drives in their signups, and then so we've got a link there for our motor drive playlist, so you can go check that out. But yeah, download that handout and this information. These links are all live, so you can just click on them and you'll end up where you need to go.
Okay. I have there was one question I wanted to address that came in from, I think it was Cameron Stewart, who's working at Tesla.
Right.
Do you really need Bodhi plots? Can you do everything in the time domain? And this is part of the content that I was going to give at APEC this year. It's a buck converter, but it's got an extra LC filter. It's got an input filter, and it's got 8 state variables. It's actually got 9 or 10 in the current mode model, depending how complex you get. If you do AC winding resistance, it's a 23 state variable. If you do core loss models, it's 46 state variables. Now, if you give me a second order converter and you say time domain, frequency domain, it's like, yeah, okay. But for me, if I've got this going on in my converter, this is my time domain simulation, I have no tools for debugging this and fixing it. And that's where the Bodhi plots really come into their own. So they're all different tools. They're all things, you use whichever one gets you to the endpoint fastest. And stabilizing this particular system, which is a really complex system, it's like for the 9th order basic current mode system here, I don't know how to do this time domain. I do know how to solve this in the frequency domain. So that just answering that one question that came in. Do we have any more questions, Albert?
Yeah, so there was a couple other questions with regards to AC/DC converters out of RidleyWorks. And then there was another, you didn't answer the question from David properly. He says, please explain how 16 bits is important, but maybe that's probably addressed on an offline email with him. And then there was the other questions with regards to some of the more variable frequency style controllers like constant on time or DCM or CCM style stuff.
Okay, if you're interested in the constant on time, go read the book. Okay. I mean, the bottom line of constant on time is it's not really very interesting. There is a small gain difference, and then you don't need the compensating ramp to stabilize it. But it's just a small shift in gain. So my approach to doing constant on time, instead of generating the complex small signal model for it, which will take you a PhD level of effort, if you're doing a different type of constant on time to this, generate it in RidleyWorks as a regular constant frequency. Set up the frequency such that it corresponds to your different cases, full load, light load. So try those two different frequencies. Export the model, all designed, swap out the controller inside LTSpice or Psim. And sweep the loop there, and you'll find there'll just be this small gain shift between the two. For me, it's not worth going deeper. If you really want to do worst case analysis, the question is, well, how much time do you have to explore it properly? You know, if you've got a few months just to do the analysis of the small signal part of it, go for it. We can help you. I just change the control and measure the loop, ship it out the door, quite honestly. That would be my approach. But it's here. It's in this current mode book. Constant on time, constant off time, discontinuous mode, continuous mode. Everything is in there if you want to dig in and get the models. So you can export out LTSpice small signal models, put in the modification for constant on time, constant off time. Just a gain change. That's all there is in there. And then fairly easy to deal with. The problem with controllers is that every controller has a different way of working. So if you start using peak and valley PWM controllers versus just a peak controller or a valley controller, the small signal models change. If you do constant off time, constant on time, and then varying both of them, nobody's even done the small signal models for half of these things. So this is where the power of the Psim sweep comes in. You put that controller in there, sweep it. If you want to do a PhD dissertation, go write the PhD dissertation. If you want to get your product out the door, because that's what you're using, do a lot of sweeps. It's just as good as a worst case analysis, quite honestly. Okay, and a lot less math CAD, a lot less pain for you in you know, doing the sweeps versus the, you know, the actual analysis. So one thing we wanted to get to, we haven't gotten to right now, working between, you know, Psim and I, is we want to have these parameter variations. Okay, change the L over this range, change the C over this range, change the frequency over this range, and then you just set up Psim. You know, if it's only doing a couple of seconds for a full sweep, you set up 100 sweeps. You let it sit there and collect all the data. That's powerful worst case analysis. You present that to your manager or the contractor or whoever. He said, yeah, these guys have done their due diligence. To me, that's much better than hand analysis, you know, or MathCAD analysis, because the models are always approximations. Even the best model, they're approximations. Sweeping the circuit is actually closer to reality, which is surprising. As someone who writes small signal models, and I did the current mode model, I'm now saying, okay, well, the actual model is what you measure on the circuit. The predicted model says, yeah, we're about in the ballpark there, it's working properly, but we're gonna have to go with that measurement to get that last little bit of detail. And that's always true. Of course, if you're doing LLCs, I don't think anybody yet has done the explicit small signal model. It is a numerical model. So there you go, that's where Psim comes in. You can grab our AP300 model all set up, ready to go, just drop it onto your LLC converter, sweep the circuit. And we've got the threshold levels and the filtering all set up properly for you, ready to go on that. More questions?
Yeah, there's a few questions. I think there's one here that's interesting, which is getting into higher power converters with RidleyWorks. So he's talking about 10 kilowatts. And I don't know if necessarily RidleyWorks can do, you'd want to do one of the topologies that you have at 10 kilowatts, but you could probably set up, say, 5 five of them to do 2 kilowatts each, and then stitch them all together and piece them and simulate the whole thing.
Oh, no, let me address that, because that's really important. Yeah, one thing I didn't address is like, okay, you've got this fantastic designer here, but I could go to TI and get their free little design spreadsheet. It's like, sure, you got to start with their controller, which to me is the last thing to grab. With the semiconductor companies, choose our controller first, then we'll help you design it. But it's baby power. It's up to maybe 50 watts. They're dancing around 100 watts these days, but you don't have the designer for it. We're not power limited, so the biggest converter we've designed in here is about 20 kilowatts. The only reason we stop there is because there's a fundamental shift in design strategy. You go 100 kilohertz or 200 kilohertz down at 100 watts, and you start dropping down. When you hit 10 kilowatts, you can still be doing 20 kilohertz, maybe 50 kilohertz. When you get much higher than that, you make this quantum change. Okay, I'm not going to switch at 100K anymore. I'm going to go down to 5 kilohertz. That's where when you hear traction drives, trains, you hear the whine of the switching converters going on. So there's that break between high frequency conversion, low frequency conversion. But there's no limits in here. Ours is completely unpower limited because we're not choosing the controller ahead of time and say, well, that can only do this much power, because it's got a driver in there, it's got the FET embedded in it. We're completely, to me, the big deal about power stage design these days, it's not about the controller. It's not even about the silicon anymore. If you want to buy a FET, there's 200 different FETs you can use. And at the end of the day, it doesn't change much of your power supply design. You just slap it on the board, you drive it, you put your heatsink on it, that's it. So what you're really down to is the passives. What does that transformer look like? What does that inductor look like? What does the capacitor look like? That's what power electronics design is really about now. And then at the end of it all, you say, well, okay, I'm going to use these switches with the right on resistance. I'm going to use the controller that will work at that frequency range and give me the features that I want. But the size of the converter is transformer, inductor, capacitors. And everything else kind of shrinks and disappears. So, we're not power limited there. However high you want to go in current in these inductors and transformers, it will go there for you.
Yeah. And, just adding in that if someone wanted to do multiple power stages and work them all together, you could design all those individually in RidleyWorks, export them out, and then stitch them all together and piece them afterwards and see how they all work together.
Yeah, absolutely.
And then the other interesting thing, once you get into Psim as well, which kind of separates from the SPICE side, is in Psim, we do have switch models that allow you to use datasheet information to do thermal losses. So if you're starting to get into situations where you care about the heat sinking and the junction temperature, those devices you can do those sorts of simulations in Psim, and they do run at the sort of speeds that we've been watching these simulations work at.
Okay.
Let me just kind of review a lot of these. I think we've covered a lot. There was questions about sweeping parameter sets, which we talked about. We talked about, there's some people saying hello from 1999 from a test talk that maybe you gave. There's PFC stuff that was asked. And I think, did you talk about the PFC stuff yet?
Didn't do that. So basically you can do many things with these approaches, but if everybody on the webinar here buys a copy of RidleyWorks, get yourself a Ridley box too, we will do all those things.
Yeah.
If you just want to look back and say, well, that's nice, but I'm not going to spend any money on that or this or that, and I'm not going to buy Psim, it's like, well, okay, so you live in the world of LT Spice and you will always, have that design phase being much longer than it should be. So as you're all stuck at home, if you get our software, one thing we do for everybody is we support people with their power supply design. You'd be surprised how much work we do for them once they're inside the family of having the software. And they will send us the files from RidleyWorks. We'll run the procedure. We'll go, okay, do your transformer this way, and we'll change the windings to a foil or something like that. Send it back to them. So we do a lot of, just washes over into our consulting as well. And whenever we do a consulting job with someone, the first thing we do is like, right, we're going to give you RidleyWorks as part of this job because we don't know how to design fast without it. So we get in there and, we work on a common framework. And then we'll always export it to an LT Spice that they can give to their colleagues at work because they want to see the LT Spice. So that's where that part came. So interesting enough, you know, LT Spice has always been there. I never used it until 2 years ago because I hate programming up LT Spice. I realized I needed to use it, but I didn't want to do the work. So then we had an engineer come in. Art Nace is his name, from Phoenix. I think he's on the call here.
Yeah.
And he wrote the interface to LT Spice for us. It was an amazing piece of work. And I use LT Spice every day now. And then Albert came in, he's written the interface to Psim. I will be using that every day now to generate these cases. So getting the LT Spice and Psim populated with a working converter is a huge, huge step in your design process. Don't underestimate how much that can change your design life. You shouldn't be worried about convergence and what kind of switches and doing this and doing this. You shouldn't be spending a week getting your converter to run. You should be spending 3 minutes to get it to run. And then you're designing. You're actively putting in those extra circuits that you need. And that's fun. That's the fun part. Fixing convergence is not fun.
No. Okay, so everyone, I think, well, we've kind of gone over a little bit here, but there's still people here and there's still people asking questions, but I think we'll kind of wrap up soon. So come up with your last few questions, and then we'll sign off and let everyone get back to their day here.
We have nothing else to do, Albert. Everybody's at home, so.
Yeah.
As the questions come in, we'll stay here if you like.
What if, so there's a question about unsupported topologies and you would like to simulate the passive parts calculated by RidleyWorks. So I guess that's using your tool for magnetics design without, without doing a power supply.
Yeah, I do that all the time. If I want to design just an inductor, I just throw a buck converter in there. Okay. And I look at the waveforms in that buck inductor and I go steady state here, continue, and then I zoom in. I'm turning the dial on the time base here, by the way. It'll get there. Here's my inductor current. So you just set up your buck input and output voltage to give you the waveforms you're going to see in your inductor. Go use the Inductor Designer. It's all there ready for you. And you've got many opportunities. So you can go in there, you can do the proximity loss. You can even, if you're doing an external inductor for an LLC, you can do that inside RidleyWorks. You can look at, you know, a foil inductor or low number of layers. You can look at a spiral inductor to see which one comes out best. So yeah, I do this all the time. Sometimes somebody's doing a topology we don't have, and it's too obscure to want to do it. So we'll just use it for the magnetics part of the design, because that part is really powerful. Exactly.
There's a question for recommended. So there's a question about active clamp forward, if that's going to be included. But I think you were saying, we said at the very beginning, those 9 topologies that you work with, you are really covering sort of 90% of the space.
Yep.
And then there's the Litz wire.
Let me address the active clamp forward.
Yeah.
The reason we don't have it in here is because there are 10 different ways of doing the active clamp forward.
Yeah.
We can't possibly capture everybody's design methodology. So design a forward, drop it into Psim, design your active clamp in Psim, sweep the circuit if you want the small signal, whatever you need to do. That's why we're porting to these other programs, so you can create any kind of clamping, snubbing, anything you want to do, you can then do that. But the fundamental operation of the active clamp forward is not really very different than just the normal forward converter. But you'll use LT Spice or Psim to capture the clamp waveforms for you in the circuit. The question there came up, Albert, is the question and answers, will they be available as well?
Yeah, so the whole recording is available, and I think part of that recording will be the Q&As. Well, this Q&A session is being recorded, so it's going to be part of the recording at the end.
Right.
yeah, so Sarah just answered that. There's, I mean, I don't think we'll release the question chat because there's a lot of there's a lot of stuff that is like, is my sound working type stuff going on, so we won't release the chat here.
Right.
Because it'll just, or we'll kind of go through it potentially and kind of get rid of the ones that are not
Right.
Wayne.
Do you send out a follow-up questionnaire about what people liked, or?
Yeah, so there should be there's a survey that
Yeah.
that people get when they exit.
Okay, if you could survey what topics they want in the future.
Yep.
I mean, we can spend, as
That's
like,
part of
this
it. Yep, that's part of it.
could be an 8-hour seminar easily.
Yeah.
Just on the magnetics.
Yeah, so I'm just going through here. Interested in ensuring the controller model is properly incorporated in the buck boost converter. And then there's one asking if RidleyWorks supports a chook. And then there's if you're going to go in and if you'll have plans to incorporate a Litz wire for the magnetics at all.
Yeah, that's all in the plans. Buck boost converter, absolutely. The 4-switch buck boost is a very important topology.
Yeah.
And this is one with 4 switches here, 1, 2, 3, 4. These are shown as diode. That just means they're synchronous rectifiers that turn on at the right time as though they were diodes.
Mm-hmm.
So I do use that topology quite a bit, as do many people. Do we do a chook? No, we're not going to do a chook. If we put the chook in there, I think we'd increase our market share by, 1 customer, quite honestly. Yeah. So for the amount of work that would take, it's just not worth it. The CPIC would be nice too, but again, it's there, it's interesting, but it's not our focus right now. We try to do the bread and butter converters.
Yeah.
People are just building lots of these kinds of converters. We're going to help you with that.
Yeah.
Part.
And it's, to be clear, with Psim, the way the sweeps work with Psim is it is a black box in the sense that as long as your system has a steady state, we can sweep it. We can introduce a perturbation and we can measure the gain and phase response at whatever node or point you're interested in. We don't care what number of switches you have, what controller is in there, how many inductors or capacitors or whatever, as long as it is stable to a transient response, it will give you a sweep.
There is the catch on using this method. You can't sweep an unstable circuit.
Yes.
Okay, if you're in Simplest has a function of getting the small signal from the large signal. You can't do it for an unstable circuit. Yeah. If you're on the bench, you can't sweep an unstable circuit. You have to stabilize it first. Yeah. That usually means pushing down the gain, then sweep it. Yeah. So if you're in Simplest or Psim or LT-Spice and you've got to push the gain down a factor of 10 or 20, and the transient response is 50 milliseconds now instead of 10 milliseconds, LT-Spice has no chance. Yeah. Psim has a chance, but you have to play these tricks as well. So using this function of sweeping, it takes skill, and it's the same skill as running, an analyzer on the bench. I go to a lot of companies and I ask them, have you measured the loop? And it's like, no, and I'll go there and they'll have a frequency response analyzer, like an old Venable sitting on the bench. No one remembers how to use it because it's a skill, it's an acquired skill. So play with this, play with the LT-Spice version, and because that one's free. And then when you've got that and you want the better speed, then you go to Psim and you have a lot of fun with this. This is a very cool toy to play with, and a very cool practical design tool as well.
So a couple more questions about sweeping. So a question, can we sweep an unstable circuit in open loop? And in Psim, the answer is no. So there's 3 different methods of sweeping in Psim. Our original sweep runs 60 cycles, and if a steady state hasn't been detected inside of 60 cycles, it will give up and move to the next frequency point. There's another one that Ray doesn't like, which is a copy of what Simplest does as well. So it's called the multi-tone or the multi-sign, where you inject a bunch of frequencies in one cycle. That one, can do a little bit better in unstable systems because you're limiting the damage to one cycle. So, but it also can give you false results as well.
Well, to say that you can't, you can actually, if you have an open loop buck converter and it's a very high Q circuit, it's going to bounce around.
Yeah.
But you can sweep that even with the bouncing around, and if your sampling is enough, and your bandwidth is okay, yes, you can get some numbers from it.
Yeah.
But there are times when, when I do that complicated buck converter circuit there for you, I couldn't possibly sweep that in Psim and make any sense of it and control the circuit. So you have to generate the small signal model and extract the Bode plots from that, then do the design, and then go back to the sweep. So there's an interesting thing happens if you want to do the open loop of the power stage. It works much better if you close the loop on it first, which we do in RidleyWorks. Then you can sweep the open loop at the power stage. If you just sweep it while it's bouncing around uncontrolled, then as I said, it can be a lot more computationally intense on that.
Yeah. So there's another interesting question here, which is I'm using the word unstable in the sense that the output is like very underdamped. It takes hundreds or thousands of cycles to tamper out, or it starts to oscillate and go and hit resonance. Those are different in my words from a stable, a circuit that has steady state is something that has a repeatable waveform from one cycle to the next. So it doesn't have to be DC. So Psim can still extract injected frequencies from a sweep as long as the cycle by cycle is the same from the one before. So there could be extra frequencies involved there, and those things don't matter. So you could run a closed loop sweep on a PSC in Psim. You're going to see a bump at around the line frequency or twice the line frequency because there's going to be extra signal there. But otherwise, you're still going to be able to generate those sweeps in Psim even with the 60 hertz signal coming in. Or you're doing
this is becoming an important question these days because people are building more and more efficient converters.
Yeah.
It used to be 70% was pretty good for your power stage when I started in this field. Now we're talking about 99.7% for some people. So when you're plotting the LC filters here you can see we got a Q of 3. You might have a Q of 10 or 20. Then you got a problem with dealing with that. Because as soon as you inject a new frequency, it excites that resonant frequency, and you got to wait for the whole thing to die out. So this is becoming more and more of a problem as we get much better caps, much better inductors, much better switches. The efficiency is going up. Systems are very undamped.
Mm-hmm.
Okay, so yeah, it's just add this to your skill set. Remember, don't be upset that these things are tough because that's why they need us as designers. Two switch Flyback, is it available? Well, I use that all the time myself. We plan on putting that in there, but frankly, the design process is exactly the same. So generate a one switch Flyback, keep it less than 50% duty cycle, dump it into Psim, generate a two switch forward, dump it into Psim, cut and paste the switches from the forward to the Flyback. There's your two switch Flyback. It's so easy. You can do that in about 5 minutes now.
Yeah. There's another question about digital control. Ray, how does RidleyWorks handle digital control? Then I'll talk about how Psim handles that.
Well, we don't. All we do is you can turn on digital compensation if you like. And you'll just see delay coming in at the end. Okay, so you can talk about the delay. So how many samples you wait here? If it's a one whole duty cycle delay, you see a lot more phase delay in there. If it's two switching cycles, you see there's no phase margin left. That's about as far as we go because there's just so many ways to do digital these days. We leave that to you, quite honestly. At the end of the day, you have a little control card. You got a little tiny chip on it, and you put analog in, and you get a duty cycle out. I don't care if it's got comparators in it or whether it's got code in it. Okay. The power stage design doesn't change, and that's mostly what we do. Mm-hmm. So it looked for a while that, maybe TI's C2000 processor was going to be like, oh, that's the digital controller that everybody uses. But every time we do a digital design review, they've got a different processor in it. Everybody's got a different processor,
Yeah.
So it's such a absolute, can of worms trying to capture that. We let the digital experts handle that. So maybe that's Psim generating code for people. I don't know.
Yeah, so the digital world for Psim is a pretty in-depth, is a pretty broad space for us. And definitely, if we cycle back to sweeps, you can do a sweep in Psim with the digital delay and the sampling incorporated with multiple delay loops, delay aspects if you want. You could do loop gain sweeps in Psim with different loops working at different execution rates, so that discretization is possible, like proper Z-domain discretization, where that signal path only executes at that interrupt rate. And you can do S to Z conversions with bilinear or backwards Euler. There's a conversion tool for that to convert your whichever control system you want, so that you have Z-domain ready code or a controller. And then the whole implementation path down to the control system that you implement. We support C2000 processors from TI pretty extensively with regards to their with our code generation, and that family has some really interesting functionality where you can mimic, peak chromo control of an analog circuit quite nicely with a digital reference. And you can do things like active secondaries on a transformer isolated system. But yeah, with digital control is something Psim really has a broad scope of. The LT Spice world is just analog power supply design, whereas Psim gets out into digital motor drives, renewable energy and all that kind of stuff. Yeah, so then, and that's the kind of thing that handles with Psim.
Right. Just a warning there for everybody. Don't look to Psim or anybody to give you the code to put into production. It's there to do the simulation of functionality. Code is worth what you pay for it. If you got free code, you better not ship it. It needs its own due diligence.
Yeah, I mean, to that point, we've had people maintain handwritten code and Psim generated code, and they've given up on the handwritten code after they've gained confidence with Psim generated code, because Psim generated code is purely a conversion of the control. We're not handling the other stuff. Right. But Sarah's saying we should probably shut down here pretty quickly. We're starting to get emails coming in.
Let me get just one more question. Yeah. Why do we still prefer using the Flyback converter? There's more efficient converter topologies. It depends how efficient you want. So when we do our lab, we build a 25-watt Flyback and we get about 93% efficient out of it. So we can build that in an hour. If you want to build an LLC, you're going to be there for a few weeks doing the same job.
Yeah.
Just to get a few more percent efficiency. So it all depends where you mean, it's not just cost, it's speed of product development that keeps these topologies alive after all these years.
Mm-hmm. So Sarah, do you have anything else you'd like to add on here before we sign off? And we'll obviously, it looks like there's a lot of topics that have come through in the questions that could spawn additional webinars here in the next few months.
Yes, we will have 2 webinars per month in the next few months, as long as we're all working from home. And then at some point we might go back to 1 per month, but I think we're also planning to collaborate more with Ridley Engineering. If you guys have interest in other topics, please email us, send us your requests, and we will try to make you happy and help you out with your questions. So please be in touch, but we cannot stay forever today. We will plan another Q&A session or another webinar sometime soon, and just please let us know what you would like to hear from us. And follow us on LinkedIn, join the Facebook group from Dr. Ridley, and then we wish you all the best and see you next time.
Yep, everybody, thank you for listening. Stay safe, and we'll see you again on another webinar.
Yeah, this was a lot of fun, guys. Thanks so much for coming by, and Yeah, Ray and I, well, Ray definitely is on his Facebook group quite often, and I hop in there whenever someone invokes me. And stay tuned for more webinars. I think this was a really fun use of time.
Thanks, everybody. Goodbye.
All right. Goodbye.
Bye, everyone.